So what I'm going to do in this video is give you an introduction to quadratics. Quadratics are a very fundamental part of Algebra I, and they're a topic that will likely follow you throughout your whole math career. So these are a very crucial topic, and this video will hopefully just give you an introduction to this crucial Algebra I topic. While the name might suggest it sounds like something very scary or something that's very difficult, I hope this video will give you some more insights into this topic and help you progress so that we can learn more about this crucial topic in the rest of this course. And I hope this will give you some clarity and show you that while this topic may sound really hard, it is not. So first, let's begin at the very beginning. What are quadratic equations? Well, quadratic equations are polynomial equations that have a degree of 2 and are often modeled by the flight path of projectiles. This might sound like gibberish, so let's break it down. So we know that polynomials are just sequences of variable expressions. So x squared plus x cubed, x plus 2. So we know what polynomial equations and expressions are. And let's think about the degree of a polynomial. Well, the degree of a polynomial is just the greatest exponent power in that expression or equation. So if we have a degree of 2, that means the greatest degree will be 2, and the greatest exponent will be 2, meaning that a quadratic equation is an equation with an x squared term. And these equations often model the flight path of projectiles as they create a shape on the Cartesian plane in a continuous graph, which is the shape of a U, which models the flight path of projectiles. So these, as I previously stated, these are modeled on the Cartesian plane by a continuous graph, meaning it goes on forever and ever in the direction that it opens. And it is in the shape of a U, and it steepens as the x approaches both sides of the graph. And these graphs of parabolas can be either up opening, like this, down opening, like this, right opening, like this, or left opening, like this. Up and down opening parabolas are vertical parabolas, and they are functions. Right and left opening parabolas are horizontal relations, and they are not functions. In Algebra I, and for the most part in this video, we are going to be talking about vertical parabolas. We are not going to be covering horizontal parabolas. In this lesson, we're going to get an introduction to parabolas with examples and real-world correlations. The examples will help you practice and understand these key concepts that will help you progress on this topic. And the real-world correlations will help you understand their importance in the real world. Math is useless without understanding how it is important to use for problems that we encounter in the real world. So let's start off with the graphs of parabolas. So here is the graph of the vertical parabola with the equation x squared. As it can be seen, the graph steepens as x approaches infinity and as x approaches negative infinity. So as x approaches infinity and x approaches negative infinity, let's look at the graph and see what's happening. As x moves further and further out, y steepens and moves further and further up. So based on this, we can write that as x approaches infinity and negative infinity, y approaches infinity. Let's look at the domain and range of this graph. The domain, which can be seen, which is illustrated by this graph, belongs to the set of all real numbers. There is no bound on where the x-coordinates can lie. However, the range does not belong to the set of all real numbers. As we can see, from this point, which we call the vertex, the graph only moves up, and thus the range is never extended past the vertex. So, the range of this function in interval notation will be the y coordinate of the vertex which in this case is 0, and what the graph is approaching. If it's an upward parabola, then it will be approaching infinity, as we stated here. If it's a downward parabola, it will be approaching negative infinity. All parabolas have the same general shape, but the steepness and direction in which the parabola opens can change based on the equation. Also, let's make sure to keep notice of some of the key parts of the parabola. We already talked about the vertex. The vertex is the point on the parabola which is either the minimum or maximum. The vertex is the minimum point of a parabola when the parabola opens upward, as we can see on the graph in blue. The parabola is the maximum point on downward parabolas, illustrated by the graph in red. Through the x-coordinate of the vertex runs the line of symmetry. The line of symmetry is a line that splits the parabola down the middle and thus runs through the vertex. We can tell that if a line is the line of symmetry or not, as one side of the parabola can be reflected across the y-axis to the other side of the parabola. The equation for the line of symmetry will just be the x-coordinate of the vertex. So if our vertex is labeled h, k, then our line of symmetry will just be x equals h. Let's look at our first example. A boy throws his tennis ball in the air. He throws the ball and it reaches a maximum point of 28 feet before beginning its descent back down. What does the flight path model? Take a crack at this problem, and assuming that you've given it your go, let's look at it. So the boy is standing at 0 feet, as distance cannot be negative, and the point at which the ball hits the ground is not specified, so we can label that x. However, we have been given the maximum point for the parabola, which is 28. Based on this, we can conclude two things. Since it's given that this is the maximum, we can conclude that this is both the vertex and that this is a downward parabola. We know this because only downward parabolas have a maximum point. Based on this, we can sketch a graph that looks something like this. Thus, the shape of the flight path models a parabola, which is a downward parabola. This models the real-world example. As the ball is thrown in the air, the projectile loses speed until it reaches its maximum, and then gravity pulls it back down. Let's look at the equations of parabolas. Parabolas have equations which define them on the coordinate plane, just like linear functions. However, unlike linear functions, parabolas have a curvature and thus don't have a standard slope or a standard rate of change. The curvature and rate of change is always changing for parabolas, since we have an x-squared term. The standard form for a vertical parabola, like I said earlier, I'm reiterating, we will only be talking about vertical parabolas in this video, is ax squared plus bx plus c, where a, b, and c are constants, or just numbers. B and c belong to the set of all real numbers. They can be any values from 0 to -2 to 2 to 4. However, a belongs to the set of all real numbers, but a cannot be equal to 0. Let us see why a cannot be equal to 0. Let's suppose we plug in a is equal to 0 in our quadratic equation standard form, ax squared plus bx plus c. We will get 0 times x squared plus bx plus c. From here, we can simplify this to bx plus c, as 0 times anything is 0. As you can see, this is not quadratic. The degree on this equation is 1. There is no x squared term, and thus this is linear and not quadratic. Therefore, a cannot be equal to 0 if the quadratic equation is quadratic. If a is 0, it will be linear. So, based on this, and based on the slides we've talked about before, about the x squared term and having a degree of 2 in a quadratic equation, let's look at different equations and determine if they are parabolas. Take a crack at these on your own and see if you can do them. Assuming that you've taken a good go at them, let's do them together. Let's look at the first question. Is x squared a parabola? Yes, of course it's a parabola. We know that the degree is 2. And even though the b and c values are 0, they can be 0. So there's no problem there. This graph on the coordinate axes will look something like this. It's an upward parabola. Let's look at the second graph. Y is x cubed plus 4x plus 4. This is not a parabola. We can tell this based on two signs. Both that there's no x squared term and that the degree on this equation is 3. This is a cubic function, and you will likely encounter these in an Algebra II class. The graph of this function looks something like this. Finally, let's look at y is equal to x plus 4. This is not a parabola. Once again, we can see from the equation that it is not a parabola based on two facts. That the degree is 1 and that there is no x squared term. We know that the degree is 1 as x to the first is just equal to x, or anything to the first power is just equal to itself. Therefore, this is not a parabola. Let's look at the second example. In order to get a better basic understanding of these equations of parabolas, let's create equations with the following a, b, and c values. Do these questions yourself, and assuming that you've done them yourself and you've given them your all, let's do them together. So, in order to create these quadratic equations, all we have to do is take our standard form, ax squared plus bx plus c, and plug in our a, b, and c values. In the first one, we will get 1 times x squared plus 4 times x plus 91. From here, we can simplify this to x squared plus 4x plus 91. For the second one, we will plug in 5 times x squared plus 2 times x plus 4, which we can simplify to 5x squared plus 2x plus 4. For the third one, we can plug in 0 times x squared plus 4x plus 1, which is equal to 4x plus 1. We can tell that this is not quadratic, as a is equal to 0. We can tell that both by the fact that it's instructing us to use a is equal to 0, which a cannot be, or we can just plug it in like I've done here. Either method is acceptable as long as we get the answer that this is not quadratic. For the last one, we will get 3 times x squared plus 4 times x plus 0, and 0 times x, 0 times x plus 0, which is equal to 3 times x squared, and that's it. Again, for this one, we can tell that it will just be 3x squared, both by knowing that 0 times anything or 0 plus anything will just be itself, or we can plug it in like I've done here. As long as we get the right answer, it doesn't matter. So now let's move on to shapes of parabolas. As we covered on the previous slides, the shape of a parabola, meaning its steepness and direction, can be changed based on the given quadratic equation or the rule for that parabola. These are the following ways that a parabola can be affected by the a, b, and c values in the standard form for a quadratic equation. When a is a negative number, meaning in the ax squared plus bx plus c, when a is negative, the quadratic equation, or the graph of this parabola, will open downward. When a is negative, we will have a downward parabola. When a is positive, we will have an up opening parabola, or the parabola will open up. And the larger the absolute value of a is, the steeper the parabola will be in the direction that the sign is. Therefore, the rate of change for x squared versus 4x squared, 4x squared will accelerate at a much faster rate, as the absolute value of this is much greater than the absolute value of this, of the coefficient on the x squared terms. When b is positive, the parabola gets horizontally shifted to the left if it's up opening. So if my up opening parabola, when b is positive, the parabola moves to the left if it's up opening. However, if b is positive and it's a down opening parabola, it will horizontally shift to the right. Similarly, when b is negative and the parabola is up opening, we will get horizontal shift to the right. And when b is negative and the parabola opens downward, we will get horizontal shift to the left. When a is equal to 0, as we've already covered, there is no parabola. When b equals to 0, that means that there's no horizontal shift. And based on that, we know that the line of symmetry is just the y-axis, as it is splitting the parabola down the middle. And when c is equal to 0, we know that the y-intercept is the origin, since the c value is just the y-intercept for the parabola. And every parabola has every parabola has only one y-intercept. Let's practice on the shapes of parabolas. Take a crack at these problems so you can get some more practice on the topic we just covered. Sketch the graphs for the following parabolas based on their a, b, and c values. Assuming that you've given these a go, I'm going to do these first two problems, and the other two you do yourself. So the first two I will do with you. So, let's draw our coordinate axis. So, for the first one, we're given that a is negative, b is 0, and c is negative. So let's break down this problem and think what these general signs of the coefficients mean. Well, we know that when a is negative, we have a downward parabola. So we know our parabola will open down. We know that when b is 0, we will have no horizontal shift. So that means that we will have no horizontal shift, and that the y-axis will be the line of symmetry. And lastly, when c is negative, that tells us that our y-intercept will be on the bottom half of the graph, split by the x-axis. Based on this, we can draw a parabola that looks like this. We can draw a parabola that looks like this. Let's look at number 2. A is positive, b is negative, and c is 0. We know that when a is positive, we will have an up opening parabola. That when b is negative, when we have an up opening parabola, we have shift to the right. And that when c is 0, the origin is the y-axis. So, we will get a parabola that looks something like this. The other two problems, do yourself for extra practice. Now let's look at graphing parabolas. Before, we learned how to make conjectures about the shape and direction of parabolas on the coordinate axis based on generic signs and values of the a, b, and c in the standard form. Now let's do more exact graphing of this quadratic equation. To graph quadratic equations, we should plot 5 points and then use those 5 points to approximate a graph. To find those 5 points, we can just take 5 x values, in my case, -2, 1, 0, 1, and 2, and plug them into the function. From there, we will have the points, and we must plot them to be able to approximate our graph. So let's do that. For x is equal to -2, we will get -2 squared plus 4 times -2 plus 4, which is equal to 0. So our first ordered pair is -2, 0. For x is equal to -1, we will get -1 squared plus 4 times -1 plus 4, and we will get 1. For x is equal to 0, we will get 0 squared plus 4 times 0 plus 4, which is equal to 4. For x is equal to 1, we will get 1 squared plus 4 times 1 plus 4, which is equal to 9. And for x is equal to 2, we will get 2 squared plus 4 times 2 plus 4, which is equal to 16. Now we must plot these on our coordinate axis to be able to draw the graph of the parabola. Our first point is -2, 0. Our second point is -1, 1. Our third point is 0, 4. Our fourth point is 1, 9. And our fifth point is 2, 16. From this, we can approximate the graph of our parabola. As you can see, graphing is not the most accurate solution, so we only use graphing in situations where an exact answer is not required. Of course, using a graphing program or a graphing calculator is more precise, but when we have to graph by hand, we select points and we use them to draw an approximate graph to the best of our abilities. Now let's talk about one of the most important topics when it comes to parabolas: solutions and roots of parabolas. The solutions or roots of parabolas are just the x-intercepts, or where the parabola intersects with the x-axis, and we have several methods to find these solutions. Relating to the first example of the boy throwing his tennis ball, we have the graph of his projectile's flight path. In this case, the solution would be where the boy's tennis ball hits the ground, as that models the x-intercept when placed on a coordinate graph. Parabolas can have 0, 1, or even 2 solutions, depending on their equations and graphs. So, let's look at the different cases where the parabola may have these different numerical 0, 1, or 2 solutions. And throughout the rest of this video, just keep in mind that the solutions or roots are just the intersection of the parabola with the x-axis. So let's look at our first case, where a parabola will have no solutions. We will have a parabola that has no solution when the parabola's vertex the minimum or maximum lies above or below the x-axis. A vertical parabola that opens up like this will have no solution if the vertex is above the x-axis, as seen here. Since the vertex is the minimum point in vertical parabolas, if it's already above the x-axis, it will never intersect. Likewise, for downward parabolas, it will have no solution if the vertex lies below the x-axis. Since the vertex of a downward parabola is the maximum point, it will never intersect with the x-axis if the vertex or the maximum is already below the x-axis. These two graphs illustrate how a parabola may have no solutions. Let's look at the second case, where the parabola has one solution. So a quadratic equation will have one solution when the vertex lies on the x-axis. This is the same for both upward and downward parabolas. When the vertex lies on the x-axis, that will be the only place or the only point where it intersects with the x-axis. The graph of this situation will look like this for an upward parabola or this for a downward parabola. Let's look at the third case, when the parabola has two solutions. So a parabola or quadratic equation will have two solutions when it intersects with the x-axis in two places. And this is the maximum number of solutions a quadratic equation can have. A downward opening parabola, such as one that looks like this, will have two solutions if its maximum point or its vertex lies above the x-axis. As you can see, if its vertex lies above the x-axis, it will have opportunity to cross the x-axis at 2 points, here and here. An upward opening parabola will have two solutions if its vertex lies below the x-axis. As you can see, this is the minimum point for the parabola. And since this is the minimum point of the parabola and it's below the x-axis, as it travels up with these two strains, it is bound to hit the x-axis at some point. Now let's talk about solving quadratic equations. So quadratic equations can be solved in many ways, and when we talk about solving a quadratic equation, we talk about finding the solutions or x-intercepts. We have many methods to do so, such as completing the square, factoring, quadratic formula, square rooting, and graphing. And these are some of the most important methods used when it comes to quadratics in Algebra I. In the following videos of this course material, we will be talking about each of these methods so that we can get a better understanding of quadratics. This was only the introduction video, but in the next strain of videos, we will be covering these 5 methods, which are crucial to truly understanding the fundamental concept that is parabolas. I hope this video gave you more insight onto this topic and gave you some clarity. Please remember to hit the like button or the dislike button and leave us a comment regarding what you thought about the videos and anything we can improve. Also, feel free to leave us a comment about any new topics on math or science that you feel we should cover. Thank you, and please subscribe.